Welcome to GATE CSE. In this video, we will study about some special matrices, which helps us in reduction of our dense matrix to sparse matrix. The first one is idempotent matrices. So, what is this idempotent matrix? It says if matrix A, if I take the square, then A square is equal to A. So, A square, if I get the same matrix by squaring it, then it is a idempotent matrix. What are the properties? Eigenvalues are always 0 or 1. Okay. I minus a subtracting a from I is also idempotent. That means if a is idempotent, then I minus a is also idempotent. If a is symmetric, okay, we already studied symmetric matrix where the elements have on the either side of diagonal elements are same. Rank of a equal to trace of a if it is symmetric. Where it is used in regression and projection onto column space. We'll come to this. Now let us take an example. So they are given this matrix, check if it is idempotent. So how will you check? To perform a square and then check if it is equal to a. This is a into a. So this a square will be equal to row into column. So by seeing only you can write the answer 1 into 1. So it will be 1 plus 0. Then first row, second column is 0. First row, third column is 0. Then I will get 0 here. 0, 1, 0. Then is 0, 0, 0. This is nothing but is equal to A. Hence, it is idempotent matrix. A is a idempotent matrix. So find the rank. What is the rank? Rank is the number of independent rows. So 2 independent rows. Or for idempotent matrix, already seen, rank is equal to trace of the matrix A. Trace is nothing but sum of the diagonal element, that is 2. So rank of A is equal to trace of A. So trace of A is 1 plus 1, that is 2. One more example. Check if I minus A is idempotent. You need not convert it to I minus A and then check I minus A whole square equal to A. I minus A. So what is idempotent they are saying? If it is I minus A whole square is equal to I minus A. If it is true, then I minus A is idempotent. But to solve this, it will take much time. So what the property says, if I check if A is idempotent, then definitely I minus A will be idempotent. That is a property. So let us check. So check A square is equal to A or not. So A square equal to 1 by 3 into 1, 1, 1, 1, 1, 1 into 1 by 3 into this will be equal to 1 by 9 into 3, 3, 3. So 3. This is my A square. This is nothing but what? You will get 1 by, you can write it as 1 by 3, 1, 1, 1, 1, 1, 1. Therefore, yes, A is idempotent. If A is idempotent, then you can verify just like this. I minus A is idempotent only, we know it, but still to verify, just square this. I square minus 2AI plus A square. So I square minus 2AI means 2A only plus A square. Now I square is always I only. I into I is I only. Minus 2A plus A square means if A is idempotent, already I've shown it, then A square will be A only. So this is nothing but I minus A. Hence, I minus A is idempotent because I minus A square is nothing but equal to I minus A. Next, projection matrix. The projection matrix P satisfies P square equal to P. It projects vectors onto subspace. What are its properties? Eigenvalues are 0 or 1. I minus P is also a projection. If P transform equal to P, it is a orthogonal projection. And rank of P equal to dimension of the subspace onto which it projects. Okay. So I'll explain it in depth. Why many of the people or students fail to understand is because they can't imagine it. So mugging up the formulas or properties doesn't help much. So it's better you understand what exactly it means. The projection of matrix P satisfies P square equal to P. That means what it is, the idempotent property P square is equal to P. What exactly it means? It projects vectors onto a subspace. Now what is the subspace? I already explained. Again, let us take an example and try to understand what is projection matrix means, why it is important. Now let us say we have 3D space. 3D space. Okay. So that means what? My space is equal to x, y, and z. Three planes are there, like three axes x, y, z. Okay. And x, y, z belongs to real numbers. Okay. So usually it's 3D space. X, y, z, they represent it as R cube. Means 3 dimensions x, y, and z. Now, if I draw a plane, how it represents? Is represented something like this, 3-dimensional. Three-dimensional plane. So let us say this is z, this is x, and this is my y-axis. This is my 3D plane. Now, what is this projection and what is this vector? So let us say there is a vector P, the column vector. Let us take it is say 5, 3, and 0. Vector means it's a row or a column in your matrix. That's what you can imagine as of now. So vector 5, 3, 0. Now, what is projection of V? Okay, let us say there is a matrix P. So let us say this is a called as a projection matrix. So this we have three-dimensional. That means there are x, y, and z three axes. So let us the matrix will also have, it will be a 3 cross 3 matrix x, y, z. So let us write this x, or this represent x, y, z and x, y, z. Here, rows and columns. Now this matrix, applying this matrix to vector V will give you projection of this vector V. Okay, that we call it as projection of vector V, PV. So if I apply this matrix P onto my vector V, okay, I will get projection of this vector V. That is the meaning, that is the projection. So what the property says, P square, applying it 2 times on my P square equal to P means, let's say PV, first time I apply the projection, then again I will apply the projection. If I apply it any number of times, 2 times, then I will get the P only, the same projection matrix. Okay, so what it exactly means, or you say V. So now let us imagine this. This is a vector. For example, I have taken 5, 3, and 0. Means what? X is equal to 5, y equal to 3, z equal to 0. Somewhere this vector is somewhere here, like imagine like this. So on z axis it's not there because z is 0. So it is on the xy plane. So this is my xy plane. Okay, now This is my YZ plane. Okay, this plane. And I have XZ plane. This is my XZ plane. Okay, this vector is X and Y. That's why it is here, right, in this plane. Now, what is the projection of this means? For that, let us imagine, okay, there's a person standing in a sunlight. So you are viewing him in 3D, right? You are viewing a person, whatever you see in this real world is a 3D. So he is present on all the three axes. Okay. Now, if I put a sunlight or a light, say a light on him, his shadow say falls on X and Y. So X and Y. See what it is, his shadow falls somewhere here. Okay. So if this is a vector, okay, the projection means you can in this example consider it as his shadow. So when I project this vector, so I'm projecting in XY plane only. Now suppose if I want to study this vector, see what is projection? Projection you can imagine like this. So this is the image. Image is falling in XY. So there is Z axis also, but the image is not on Z axis. That is what you are imagining. So I want to study only in X and Y axis. Projection of particular space is XYZ here. So projection, I want the projection of that vector in only X axis or on only Y axis or only on Z axis so that I can study it properly. So I am studying the concept of this and I want to study it properly but each of the axis separately. So that is an example I am giving. So the projection vector means I can project it on any of the axis. So that matrix which helps us to project is a projection matrix. Now in this example, let us say I will take this projection matrix as I want to project it on X axis only. So let us write my subspace. So my space is what? My space is in this example is X, Y, Z, three-dimensional. So what are my subspaces? So let us say there are many subspaces possible. So let us say X is one of the subspace, Y is another subspace, and Z is another subspace. I want the projection of this matrix. This matrix is in both X and Y. X, Y, Z. With 5, 3, 0 means it's not there on Z axis. It is present on X and Y axis. Now I want to study this vector by projecting only on X axis. So how will I do it? So what the projection matrix does, it says you put, because I want to view only on X axis. So X will be 1, set to 1. Then Y and 0, I don't want to study 0. So 0. So 0, 0, 0. So let us say this is my projection matrix. And my vector is 5, 3, 0. So let us see the result, what I will get. If I apply this P 1, 0, 0, 0, 0, 0, 0, 0, 0 onto my vector V. What is V? 5, 3, 0. So I will get my projection vector PV is equal to 5, 0, 0. Okay. So this is the concept. Hope you are getting it. Now what they say, projection and on the projection. See if I apply one more time projection on this matrix. So same P into it is 1, 0, 0, 0, 0, 0, 0, 0 into 5, 0, 0. I will again get the same matrix, same vector back. P. So this is why we say it is idempotent. P square is equal to P. It does not change. See, for example, here the image is here. The image is here. Once I am putting a shadow, and that time if I put a shadow, it is on the same shadow only. So there is no change. So that is how you study the systems using the projection matrix. Now, what are its properties? Eigenvalues are 0 or 1. because the projection matrix is something like this. If I take the eigenvalues of this, it will be 0 or 1 only. Then I minus P is also a projection. What is I minus P? Subtracting projection matrix from I. So I is, for example, 1 0 0 0 1 0 0 0 1 minus P 1 0 0 so 0 0 0 0 and 0. So this will give me 0 0 0 0 1 0 and 0 0 1. If you observe here, this y and z is given because 1 is set here. This is x y z. Previously it was 1 here, so x axis. Now what it means? This will give you the projection of the same vector on y and z axis. Projection of the same vector on y and z axis. Same matrix. Okay, that is the meaning. So if you apply something, some properties will change. It is all about what you are studying here. See, on x plane how it looks like, on xy plane how it looks like, on x axis how it looks like, on y axis how it looks like. So that is, you are studying the complete dimensions of the system. So that's why you use this all kind of special matrices. I hope you got this. Then if P transform equal to P, it is an orthogonal projection. If I transform that matrix, I'll get the same matrix. For example, if I transform this, transform of this is the same matrix I will get. It is this projection matrix. That means what? It is an orthogonal projection. So why it is orthogonal projection? Because all these axes are perpendicular to each other 90 degree. This is the reason why you will get an orthogonal projection. How you view it, the vector is what is orthogonal, right? You are viewing it at the right angle to the vector. That is the meaning of it. Now rank of P is equal to dimension of the subspace onto which it projects. So for example, what is the dimension of the subspace? Here I have taken dimension of the subspace is only one axis, that is 1. Dimension is 1. The rank of this will be also 1. See, its rank of this we see is also 1 because only one linearly independent row. Okay. That is the concept of this all projection, space, subspace. We'll take a simple example. Check if it's a projection matrix and find its rank and eigenvalues. Now, how will you say it's a projection? Again, the square of this should be equal to P. So we will take 1 0 0 0 1 0 0 0 0 into P. This will be, we'll get it as 1 0 0 this row and this row, this column. You will get here as 0 1 0 0 0 0. So only if we see here x and y are set. So there are two subspaces I have. So what is the rank? It's a projection matrix, so its rank will be number of subspaces, that is equal to rank equal to 2 for x and y plane. Okay, x and y axis. For the eigenvalues will be either 0 or 1. So if you calculate the eigenvalues, you calculate 1 minus lambda to 1 minus lambda minus lambda. So it will be 1 minus lambda into 1 minus lambda into minus lambda minus the submatrix is 0 equal to 0. So that is 1 minus lambda square into minus lambda is equal to 0 or lambda equal to 0 or lambda equal to 1. Okay. Now verify if it is a projection matrix. Is it an orthogonal projection? What is the orthogonal projection definition? So if it is orthogonal, if P transform equal to P. Okay, so now we've done it already previously. So p square is equal to, I will get p only. So if I do multiply this matrix, okay, if I find p square, I will get p only. So it is a projection matrix. Is it orthogonal matrix? So p transform is equal to, if I transform this, I will get again same matrix. Okay, so therefore it is an orthogonal projection. Next, check if I minus p is a projection matrix when this. So already you know, first only thing is you have to verify whether p square is equal to p for idempotent also, for projection also. If this is true, then this will always be projection matrix. You already seen this. If you find this, then this will also follow. Okay. Next is another type of matrix called as orthogonal matrix. A square matrix Q is orthogonal if Q transform into Q equal to I, identity matrix. So if that is true, then what is Q inverse? You send this T that side. Okay, or so Q inverse means Q inverse or QT is equal to I into Q inverse. So that is nothing but Q inverse is equal to QT, Q transform. The determinant of this will be equal to plus or minus 1. Rows and columns form orthonormal sets. The orthogonality means what? You are rotating by 90 degree clockwise or anti-clockwise. So in your plane, so this is my x, y, z. So suppose there is a some vector here. This is in both all three x, y, z plane. So x, y, x, z, x, y plane and this plane. This vector is there on all the plane. Okay. Now, what is this orthogonality means? If I rotate this by 90 degree, okay, if it was like this, make it counterclockwise 90 degree, this or this. So now how, by transforming it, what are its properties, how it changes, that is what you study using orthogonal matrices. So rows and columns form, so of your orthogonal matrix, if this matrix is orthogonal, its rows and its columns, whatever you get, are called as orthonormal sets. And then eigenvalue satisfy lambda equal to 1, that is can be plus or minus 1, but we say only dimension 1. Preserves the length of the vectors. So the initial vector length will be equal to the orthonormal sets vectors. Okay. Now more on that I will explain when we take vector spaces. So now as of now, for basic linear algebra, these concepts are sufficient. So that this is an orthogonal matrix. For that, what is the condition? So condition is multiplying Q transform into Q equal to I. See, Q transform comes first. Qt into Q may not be equal to Q into Qt. That is your commutative on matrix multiplication is may not be true always. May not be commutative always. So what is Q transform? Q transform is change rows and columns. So this is 0, 1, 0, 0, 0, 1, and then 1, 0, 0. This into Q. Now Q in Qt into Q. Q is 0, 0, 1, 1, 0, 0, 0, 1, 0. This should be equal to what? Identity matrix. So this is what you have to find out. That means it has to find out. So if you multiply, so it is 0, 1, 0 into 0, 1, 0. So I will get 0 this row and this column. Okay. So 0, 1 plus 1. So it is 1. then 0, 1, 0, and this is 0. This is also 0. This row, this column. Then this row, this column is 0. This row, this column is 1. This row, this column is 0. So this is 0, again 0, and this is 1. This is nothing but my identity matrix. Hence, this is the orthogonal. Next, normal matrices. If a square matrix A is normal, if A into A transform equal to A transform into A. Okay. So, a very simple thing. So, to verify only your every symmetric, skew symmetric, and orthogonal matrix is always normal. If you find the given matrix is symmetric, skew symmetric, or orthonormal, then this is normal. And normal matrices are diagonalizable via orthogonal transformation. Let us take an example. Check if this is a normal matrix. 2, minus 1, 0, minus 1, 2, minus 1. See if it is a, they are same. Above the diagonal and below the diagonal elements are a 1 to 1 mapping. So it is what? The symmetric. Skew symmetric means signs will change. So it's a symmetric matrix. If it is a symmetric matrix, then it is a normal matrix. Okay. Or other way is to find A into A transform. This should be equal to A transform into A. To get this, then it's a normal matrix. That's a procedure. But based on its properties, if it is symmetric, skew symmetric, or orthogonal, then I can definitely say it is a normal matrix. Then next is a partition or block matrices. A matrix can be partitioned as, okay, if you have very big matrix, okay, very big, say 1000 by 1000. Now the computation becomes difficult. So what we do is we split this into different blocks or partitions. So this is called partition or a block. Okay, let us say we will divide it into 4 blocks. And then for each sub block, we apply the same matrix properties. Okay. What it says, multiplication is defined if block sizes matches. See, this block should be same, both should be same. Then only we can match them or multiply them. For a block diagonal, determinant of A equal to determinant of A11 into determinant of A2. This is what, if it is a block here, not single elements. This is a block, determinant of this entire matrix, okay, will be equal to determinant of this block into determinant of this block. Okay, that is the meaning. Useful for LU decomposition, solving large systems, and simplifying the calculations. Let us take an example. So this is a partition matrix. So to apply those properties, what is the size of this partition A? So let us say this is A1 block. A1 block is 2 cross 2. Next, this is A2 block. This is A1, A2, say A3, A4. A2 is 2 cross 1. A3 is 1 cross 2. A4 is 1 cross 1. Okay. Only check that for which block the multiplication is possible. This 2 cannot be multiplied because this number of columns in A1 and number of rows should be equal. So this is which you have to verify. This I can do it. Okay. So in the exams they may ask something like this properties. To compute block multiplication. How will you compute block multiplication? See, this A, B, C, D are not elements here. They are the big blocks. So just carry out multiplication as usual. This is A x plus BZ. Okay. Then you have AY plus BW. Then CX plus DZ. Then CZ plus CY plus DW. Okay, this is permitted only when the order, say it is M cross N, A is, then this this block A is M cross N, you are multiplying it to what? X, right? So X should be having n cross say some p. Otherwise, this is not possible. Right? Okay, so you have to be very careful with this. The number of columns in A should be equal to number of rows in X. So similarly, you can find out for all these possible combination A, Y, B, W. Okay, so similarly, Y should have say n cross say Q. Okay, then C is say P not A cross B. Then is multiplied with X. X should be, so n means it should be n into P like that. So you find out. Okay, that's about special matrices. So is I given the summary here. The projection or idempotent means P square equal to P, eigenvalues are 0 or 1, and the rank will be equal to trace if it is symmetric. Orthogonal matrix means Q transform into Q equal to I, and the determinant will be equal to plus or minus 1. Preserves the vector length. Normal means A into A transform equal to A transform into A, diagonalizable by orthogonal by unitary matrices. Okay, block matrices means determinant of A is equal to, so entire matrix equal to determinant of block B into determinant of block C. It is used to simplify the large systems. So symmetric idempotent means rank will be equal to trace. Thank you for watching. We'll solve few problems in the next video. Please like, subscribe and share.